Okay. So the last time we looked at what do you call it? We looked at reflection for plane surfaces, right? We looked at for curved surfaces as well. So plane mirror and curved mirror, we looked at it the last time. I will show the features and everything that we need to know regarding your plane mirrors and regarding your curved mirrors, right? So that was what we did. It was more of what reflection. We started off by talking about rectilinear propagation of light, how light behaves, talked about shadow, eclipse, pinhole camera, and the rest of them. Moved over to plane camera to plane mirror. In plane mirror, we spoke about how the images are formed. These are part of the things we looked at, and then we solved some problems on that. Then yesterday we looked at curved surfaces, right? Concave mirror, convex mirror, how convex can be used as your driving mirror, how the image is always virtual, right? It's always virtual. Then and it's always smaller than the object, that's the image formed, and it's also erect. Then we spoke about your concave mirror. Under concave mirror, there are key things we highlighted for concave. We said that for the concave mirror, it depends on the position. If at the center of curvature, something will happen. At the principal focus, something happens. Between the pole and the principal focus, that means towards the focal length, something happens as well. And for that focal length, we said that that is where the image is larger, right? It is larger, it is erect, and it is virtual, right? So these were some of the things we looked at. So this morning, we'll be looking at refraction at plane surfaces, right? Now, you can see the diagram right here on the screen. You have the incident ray, right? You have the incident ray, and then you have the reflected ray. Now, for the incident ray, once it hits the medium, see that medium one, what happens? It bends away, right? So before we look at that diagram, let's look at the key things that we're looking at in today's class. So we'll look at reflection at plane surfaces, right? I'll look at the introduction, I'll define the terms, we'll look at the laws of refraction, we'll look at the effect of refraction at a plane surface, right? We also look at the deviation and the minimum deviation. So that's the very one I spoke about that I said that is a big technical, but not as I believe we have very smart guys in the house and that you guys will tend to understand that. Sorry about the noise in the background. That's my utility disturbing. All right. So we have the next one, which is the total internal reflection and critical angle as well. So for critical angle, I think we did that a little bit the other time, and some of us understood what we mean by that. Yeah, I think we did. All right. So we'll also look at that towards the end of the class. I pray that time will permit us and that internal what do you call it? Deviation doesn't take a chunk of our time because that's my only fear that deviation might take a lot of the time, the minimum and maximum, sorry, minimum deviation. I think it might take a lot of our time, but then we hope that you guys will catch up very quick. All right, so let's look at this now. So as usual, light will keep traveling in a straight line like we agreed the other time. But now, once there's a change of the medium, like we said, that is when there will be a change. When it encounters an obstacle, we are saying that there should be a change in the direction per se. So that when a ray of light traveling in one transparent medium enters another transparent medium of different what density, its direction is going to what change at the surface separating the two media, right? So now this change in direction of the light ray is what we know as what refraction. A good number of us should know that once there's that change in direction of the light, it is regarded as what refraction because of what there's a change in medium. Remember that light can only keep traveling in a straight line if there is no change in the medium and if there is no obstacle, right? So from one transparent medium to another transparent what medium, we say that refraction has occurred. So the basic thing I want you to remember is that refraction is due to the difference in speed of light in these different what media. Because of the difference in the speed of light, that's exactly what brings about the change of the direction. So this number 3 is very important. If you can forget any other thing, please don't forget this number 3. You might see questions along that line. Why does refraction occur? Because of the difference in the speed of light. So refraction can occur when light travels from what? From air to glass. You know that air is less dense, while glass is what? Is denser, which means that glass is heavier, right? So from less dense to a denser medium or vice versa, right? Vice versa, trying to say that either you're moving from denser to less dense. The same thing happens. Okay, so now let's look at this very diagram so that we can understand something better, please. If you have questions, please ask. And I hope Susan and people that complained about my speed the last time, Susan, who again complained, I think it was Confidence, right? And Ibaha, I hope that my speed is not much today. So now let's look at this. We have your incident ray. So this is the first medium, right? The first medium and then the second medium. What happens? We have our incident ray. Once it hits this is the first medium, moving from the first medium to the second medium, it doesn't continue traveling in a straight line. The direction is going to change. And the direction is dependent on something. That direction of the ray is dependent on something. So now, while we've agreed that the medium, the density of the medium are not the same, something happens. Let's see if we can model what happens at that point. Now, assuming you are traveling from a less dense medium than the one that is not heavy to a heavier medium, what happens is that the refracted ray bends towards the normal. So I should expect something that goes like this. We should expect this guy moving closer, right? How do I put it closer? This is going away. My rotation is not working. Just understand what I'm trying to say. It comes closer to the normal, right? So it is expected that as I'm going through a more from a less dense to a denser medium, that this guy will keep going closer to the normal. That's what I'm trying to say. But if I'm moving from, let's assume that the medium one is now denser and medium two is less dense. It is expected that this guy will now bend away from the normal. And that is what brought about your total internal reflection that I asked you in class the other day, right? So when you are traveling from a heavier medium to a less dense medium, the refracted ray is expected to move away from the normal. But when you are moving from a less dense to a denser medium, it moves towards the normal. Do you understand it now? A thumbs up if you understand what I just said. It's very, very key. That will take note of that. All right, Mesa has given a thumbs up. Is she the only one that understood what I said? If you don't understand, give me a thumbs down. Okay, Paul has a thumbs up. Lilian gives me a thumbs down. Nikki Gotsiva a thumbs down. Who again? Okay. Now, then no thumbs up, no thumbs down. That means you are lost, Abby. Justice and Co. That means no thumbs up, no thumbs down. That means you are lost. Okay, look at what I'm saying, men and brethren, right? First of all, we said that light travels in a straight line. However, in that very class, I gave us a condition for light to keep traveling in a straight line. The first condition is that it doesn't encounter any obstacle. The second condition is that it keep traveling in the same medium. It doesn't move to another medium. So if the medium here, medium one and medium two, if they are the same kinds of medium, it is expected that they keep traveling in that medium. They don't change. Do you understand? So they keep moving in a straight line if the medium is the same. Now, but when the medium or the media is different, you get the point now. It is expected that the direction of the light will change. Direction of light will change when there is a change in the medium, which is exactly what happens here. We have a lot to do. We cannot, if you go to minimum deviation, understand this one very fast so we can move. So now, this refracted ray now, the direction will change, just like what you saw. It bends away. Initially, it was traveling a straight line. Then all of a sudden, there is a bending, right? Do you understand what I'm trying to say now? 2 seconds. All right. So there is a bending right here because of what? There is a change in the medium, right? Now, if the medium one now is, when I mean dense, means is heavier. If I say that Meso is denser than Paul, which I don't, both of them, I think they are very slim. I don't think so. From their pictures, they are slim. But I know that women will always, okay, men should weigh more than women most times, you know. All right. So let's say that, let me use who and who. I think I've seen Nikki Good before. Maybe it's okay, I've seen Lillian as well. All right. Yeah, Nikki Good, she know the rest. I did see I most times she posts Prolo, she posts herself. Okay, so now let me use both of them. So when I mean denser means heavier. So let's say that Nikki Good is heavier than Paul, right? So let's assume that let me use your names. I think that's better now. Let's say that this is Nikki Good now here, right, being heavier than Paul. So now this is now Paul. The medium here I have here is Paul. Remember I said that gold is Nikki Gold has more weight than Paul. So what happens is that if the incident ray gets to gold, because gold is heavier than Paul, what happens is that this direction will change. And the way it will change is that since gold is heavier, what happens is that this ray you are seeing now, will start, this is what we call the normal. This line is a normal. This is your normal, N for normal. Now, what happens is that the ray will start moving away from the normal. Like it starts coming to this direction. As if it's trying to go and align here. You get my point now? If it is moving from someone that is heavier to someone that is lighter, it keeps going up. The next time, if you keep increasing this incidence rate, if this value keep increasing, that line keeps going this way. It keeps moving away. It keeps moving away. Do you get the point now? Do you understand this first part now? Nikki Good and Lily and the rest of them. Do you understand that first part now? Beautiful. It keeps going what? Going up. That's the refracted what? Ray. And remember that the angle between the normal and the refracted ray is your angle of refraction. Very important. So that is what you should always remember. Now, case 2 now. Our case 2 will now be, if I interchange, let's interchange a bit. Let's interchange. The first case was having gold up and Paul down. Let's now bring Paul up here, who is now less dense. And let's bring gold here, who is Mame Yabo. But she's not actually. She's not. But I'm just giving an example. So now, if Paul is there, so the movement is in terms that what will happen now, this refracted ray will start coming towards the straight line. The more you increase this incident ray, the more this one is moving closer to the red line. Does it make sense now? The more it moves closer to that red line. And that's what we mean by your refraction. And what happens in terms of the movement when this one is heavier and when this one is not heavier. Does it make sense now? Good. Lillian, does it make sense? Lillian, does it make sense? If it doesn't, give me a thumbs down. And at that point in time, if it's still a thumbs down, I leave you to the Holy Spirit. Titi, are you serious? Titi, what's the challenge?
Not so.
So what's confusing you?
Nothing.
Nothing, but I keep,
Mistakes.
I beg, that is
Mistakes.
a costly mistake. Be careful. All right, so that's for that anyway. So if the medium 2 is denser than medium 1, the ray is bent towards the normal as it travels from the first to the second medium. If medium 1 is denser than medium 2, the ray is bent away from the normal, right? So that's all I want you to know for this part of the stuff. All right. So now the second part of things that you should know is what happens to the effects, right? Of okay, I've done this already. I've explained this. I've done the definition already. I've told you change occurs and then vice versa, right? I think this has been done already. Definitions done. Then let's look at the laws of refraction. So that very image, what the law says is that based on this diagram here, it says that the normal, this is the normal, this line here is the normal, right? That the normal and the incident, the normal, right? The incident ray and the refracted ray, they all lie in the same plane. That was the first law of refraction. So all of them will lie in the same what? In the same plane. The second one is that the sign of this one, the ratio of the sign of this and the sign of this gives us a constant. That constant is what we call the refractive index. So when you look at it here, we have that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media. So that is what we regard as the what? As the Snell's law. So sine I over sine R is equal to N. I is the incidence and R is the what? Is the angle of what? Refraction. All right. So that said, I said something that constant is known as your what? Your refractive index of the second medium with respect to the first medium. That order of the medium is very important. And that's why I took so much time to explain the difference between the two mediums, right? So now, remember what I said? The refractive index is more like the first one, second one with respect to the first. Example, you see something like this. This is air, A and G, air and glass. Remember that air is less dense than glass. And that's why even we are denser than air. That's why we are on planet Earth. We are not floating. And any day you start floating, that means there's someone, that primary school days, someone gave you something to eat, and then at night they will call your name. Back then they say it's popcorn. You ate popcorn from, so we call it popcorn. So that means that something has happened to you, right? So now, A is air, G is glass, less dense. So now, but this very refractive index is for the glass. So this simply means that refractive index of what? Of the glass with respect to air. Please take note of that. It's going to help us as time progresses. So refractive index of glass with respect to air. So air, right? So that is what this thing represents. We write as A N G, right? So, but it means that this is the refractive index of air glass per se, right? So if someone gives you that ANG equal, let's say 1.0, know that that value, it means that the refractive index of what glass is 1.0. If you now want to get that of air, you do 1 over 1.0. That will now give you the refractive index of air. Men and brethren, do you understand what I just said? A thumbs up if you do. A thumbs up if you do. Paulo, what's up? But what's the problem?
So that what you just said now, I don't understand.
Okay, Timbela Japan. Okay, what I said is ANG, right? Simply means refractive index of glass. So if they tell you that the refractive index of glass is 1.0, it simply means that sine of angle of incidence in air over sine of angle of refraction in glass is equal to that value. So refractive index of glass is simply means what? ANG. So when someone asks you to find example now, refractive index of air, please, refractive index of air is not this ANG, because that value is the second medium with respect to the first medium. Second medium respect to the first medium. So this thing can be confusing because of this ANG. Someone will feel like it should be what? NA. Sometimes they just report this value as just NG. Sometimes they report it as NG, but someone will want to confuse, just have that ANG, which means refractive index of glass, which is what? Index of air over index of glass. There's something I said second. If I say it again, you might be confused. When we go to internal reflection, you understand what I mean better. When I said you do 1 over 1.0. For example, what I said, let me say it again, is that if I'm not looking for the refractive index of air, what I will now do, remember that what will now happen is that glass will come up, air will come down. That is refractive index of air, which will now be written as what? N. Air, glass will be here and air will be down. Do you understand what I just said now? If you understand what I said, can you give me a thumbs up? Titia understood. Who again understood? Nikki Good understood. Paulo, what's up? Good. Paul understood. Now, good. That's what I said earlier. I think I answered it in a better way. Justice, are you in class? Confidence, are you in class? All right. Emmanuel Chinonso was not in class yesterday. He's not in class today. Guys, did you check up on him?
He wasn't active in the morning.
In the morning.
He has not replied my message.
So, but it has delivered.
I think so.
Can you quickly check whether the message has delivered?
Yes,
If,
that's
if
delivered. Okay,
and he has not responded.
he has it has delivered, but he has not responded.
Okay. I will give him a call later today. Let me know what the problem is. But if message I've delivered, he has not answered. Maybe he's working. He's the PA to Dangote. The message is too much. Actually, I told someone something the other day that no matter how busy we are, there is no human being that let's for now, none of us is as busy as Dangote, no matter how busy we claim, that doesn't have access to their phone within 24 hours. So when I send message, you don't respond, two things are involved. It's either you read and then forgot to reply. But you telling me you've not seen the message, even myself, if I tell I've not seen the message, then I'm lying. You get the point? Unless you forgot.
NEPA is another factor to consider.
NEPA is okay. NEPA is another factor. Okay, delivered and the phone went off. Okay, back to, I'm going to call him after now. Okay. All right, so I've explained something about what? The sign of angle of incidence in air to that of sign of angle of what? Refraction in what? In glass. So when you now swap it, you are looking for the what? That of refractive index of air, right? Because at that point in time, you now have from denser to dense. That's when I explained using Nikki and Paulo. All right, so that said, let's continue. So the next one I want you to remember is that it can also be given in terms of velocity of light, right? So the Snell's law can come in two ways. That's why I wrote this one as my equation number one, which is sine I over sine R is equal to the what? Constant n, which is what? The refractive index. We're going to solve problems very soon. Then the next one here, right here, is that it can also be velocity of light in medium one over the velocity of light in medium two, right? Light in medium one over light in medium two. That is also your refractive index. So if the speed of light is given to you, let's say medium one is air, medium two is glass, or medium one is air, medium two is water. It's always between air, glass, water. You get the point now, right? Now you know that if you have glass and water, which one is less dense? Glass, water. Which one is less dense? If you have two medium, glass and water, which one is less dense? Let me call him. City.
Sir.
Which one is less dense, or sir? Yeah, saying sir. I wish you can understand it, but that would have made more sense.
Okay.
Water and glass. Which one is heavier? And which one is less dense?
Water is less dense.
Water is less dense. Why?
Because the density of water is lower.
You are still speaking English. In a layman term, why is you are still? If I'm a layman, I've not gone to school. How will you tell me that its density is? What do you mean by density? Anybody?
Okay, let's say glass is heavier than water.
Why? How will I know that it is heavier?
We'll measure it now. We'll carry it and see the heavier one.
Because it sinks inside water. That's what I want to hear, young lady. It will sink. That's what a layman will understand. That when you bring glass and put inside water, it will sink, which means that it is heavier. If it's floating, that means that it is what? It is less dense. Do you get the point now? So these are two medium they can use: light, air to glass, glass to air, glass to water, water to glass. So within those two. All right. I hope that makes sense. Now, effects of refraction at a plane surface. These are the effects. You can go and watch animations on YouTube. I will not have time to start explaining that. Now, a swimming pool appears to be shallower when we look down into it than it actually is. Sometimes when you're looking at the swimming pool, you think that you can just put it there, put your leg and swim everything. It is when you enter, you know that it's deeper than you imagine. Because of refraction, if you are looking at the bottom, you are seeing the surface up. That thing is deeper than that. Don't try it at home, right? Before you drink 15 cups of water before they deliver you. All right. So it is because of what? Of refraction that it appears as if the bottom of the pool is very close to the surface. I know you've seen that before, right? How many of us have seen that before? Have you noticed that before, right? That when you're looking at the bottom of a swimming pool, it appears as though it is at the surface, yeah, as if you can swim it. Okay. So now the next one is that a partially immersed straight stick that is dipped at an angle into water appears to be bent at the interface between the air and the water, right? So if you have something that, if you put a stick now partially inside water, to look as if it is bending towards the tip of the bowl, right? So these are one of those applications of your refraction. I will not go into detail to start explaining how it happens and the angles and everything. I just want you to understand that these are the two applications of it. Do you understand now? So these are the applications or the effects of refraction at a plane surface. On your own time, you can go watch. It's a very amazing concept. I think you need to know it so that when you see someone, a person will be like, this in the shallow, you can explain why it happens that way. Okay. So another one is when you place a stick inside water, it appears to be what? Slanted inside a bowl, right? Then a coin in a bowl, invisible to an observer at first, becomes visible when water is poured into it, right? It looks as though you are not seeing this is at first, please. This is at first. Then when you pour water now, it now becomes visible. It's also based on your refraction. So I've highlighted three things, and these are the three things they can ask. These are the three applications, right? Number one, swimming pool. Number two, when you place stick inside water, it bends a little bit, right? Inside a bowl, it bends, appears as if it's slanted. Then the third one happens to be with a coin. Pour water, you start seeing the coin, right? So on your own, please just watch animations, 3 minutes videos. It's going to explain those things real well, okay? So now, the next one is your refractive index can also be what? In terms of real depth and apparent depth. Because of the issue with your swimming pool, you can as well calculate your refractive index using this formula, that real depth over apparent depth is your refractive what? Index. I think this should be my equation number 3. This will be my equation number 3. Guys, are we still following, everyone? I hope it is still making sense and that we're making progress, right? Give me a thumbs up if you're following till now. So we'll move to the next. Please keep remembering these formulas, okay? So thank you. Is the only that is following? Is the only that is following? Who again is following? Okay, I shall assume. Okay, Lillian is following. Nikki Gotsiva is following. Yeah, Justice, what's up? Hope you are there. All right, so take note of those three formulas. The first one I gave you was sine I over sine R, and I spoke about the refractive index. Second one is the speed of light. Speed of light in the first medium over speed of light in the second medium. Then the last one happens to be with the what? The real depth over the apparent depth will give you the refractive index. So these are the three key formulas I've spoken about. And then let's look at the almighty deviation and minimum deviation. Now, the minimum deviation is simply how far, right, the ray bends away, right, from the original part. So how far does it actually bend away from the original part? We know, but this time around, deviation comes into play when you are considering what? Your triangular prism. Some of us that did this experiment, that didn't copy the graph. You know, there's a difference between plotting graph and copying graph. And then some of you during your WAEC, you copied the graph. But I hope that I have good guys here. All of you are good. Nobody copied the graph. Now, but this diagram is something that we all should be able to remember. People are laughing. People are laughing. Am I lying? Some persons copied the graph. I know what I'm talking about. If you know you copied the graph, can you just type amen on the chat? Just be sincere. Be sincere. Nobody will know. Nobody will know. All right. So, but I believe that if we did our practicals in school, that this very diagram should be a diagram that we've seen countless times, right? Can you still hear me? How do I check if you guys can still hear me? How do I do this? How do I check if they are still following me? I need to log in. If you guys can hear me, someone can just unmute and talk because I can't see those in the meeting currently. Hello? If you can still hear me, someone can unmute and talk, please.
We can hear you, sir.
Okay, thank you. Thank you. Because I can't see anybody currently. All right. So I was saying something that if you actually plotted graphs or if you did this experiment back in school about your triangular prism, where they say you should check, that time I will keep looking, I'm not seeing anything. So it was my classmate that was blocking those things. He will place the pin the other side and go and block. I said, oh, I'm not seeing anything, guy. What are you guys blocking? You know, so this experiment happens to be funny anyway. They will say, put the pin here, put the pin, look. What are we seeing? I mean, I'm not seeing anything back there. I don't know whether you guys saw anything. Maybe because my eye is faulty or something. But I think triangular prism was one of those experiments that people were a bit confused about, back in secondary school. But I know some persons enjoyed it, but I don't think I'm that person because sometimes you are trying to block the pin is blocking you. So now the minimum deviation is simply trying to tell you how far the ray deviates from the normal. Is that okay? That is simply what that guy is trying to tell us. So let me quickly join with the other device so that I can call names, ask questions, and know who is following and who is not. Because at the moment, I'm not seeing anybody. Like, literally, I'm not seeing anybody. I'm coming, 2 sec. All right. So I can know when to call your names, know who is following and who is not. Okay. So like I said, it's simply how far the refracted ray bends away, right, from the original direction. So this is a triangular prism. And in this triangular prism, it has an angle. And the angle is A, right? So this is the angle here, angle A. Now, that said, your triangular prism now, this is the incident ray. So when we place in our incident ray, right, our I ray on the prism, it is seen that something happens, right? And what is that thing that happens? What happens is that we are going to see something very key. Network is really, really disturbing me like badly. All right. So it tells me how far the ray moves out, right, from the normal. So look at this. This is our incident ray. As it's coming here, it hits the glass prism. When it hits the glass prism, you see what happens. On a good day, it should keep traveling on a straight line, right? It should keep going this way. But because of what we studied about in terms of obstruction of light, it's going to be refracted. Like this is the refracted ray now. This is our normal. So this is the refracted ray. So it changes the direction. So the deviation is simply trying to check how far the light bends when it passes through a prism. How far does it bend when it is passing through a prism? If you check this guy now, this is our incident ray, hits on this, then it bends away. So how far it bends is what your deviation is trying to describe in a triangular prism. This is a triangular prism, right? So how far it bends is what your deviation is trying to answer. So when the light enters, what happens? It's going to what? Refract. This is your refracted ray, and the angle between the incident ray and the what? The refracted ray is this very one. Now this is the deviation. On a good day, this guy should keep traveling on the straight line, but there's a deviation. So how did it deviate? By how far? This is your D1. Then the ray continues after refracting. So upon refracting now, it gets to the second surface and then it refracts again. So you have two refractions. The first one, R1, the second one, R2. Then instead of this light to keep moving straight up, it's going to what? Bend again. Now, this is the bending now. It bends this way. That's the bend now. Now, the deviation is how far it bends away while traveling. It should have gone this way, but look at how far it bends. Can you see it now? So this is your D2. Now, based on your vertically opposite angles, here is also R2. And the total angle from this very ray, this is your refracted ray, isn't it? Now, to the normal is what we call the emergence, angle of emergence, right? The emergent angle E. If you can remember this experiment very well back in secondary school, you could know that we normally plot a graph. We have a table for the incident ray. We have a table for the refracted ray. The one that was very difficult back then to measure was this one. Sometimes you run like it runs you mad trying to measure the internal angle, right? And then after that, you measure the outside angle, which is your emergent, the emergent angle of emergence. Yeah. So are we following now? Anybody confused? Anybody confused? Can you give me a thumbs up if you're following it now? Can I get a thumbs up? Paul is following. Who again is following? If you are confused, give me a thumbs down. Oh yeah, make it begin to fall like rain. Lillian is confused. All right. Titilola, are you confused? Nikki Gotsiva, Justice, are you? Can you keep? Nobody's answering again. Let me know what I'm doing, or should I proceed with just Paul? Paul said he's following. Okay, Nikki is following. Interesting. Nikki, that means she did this experiment back in secondary school. Titi is following. Makes sense. Justice, are you following? Lillian, tell me the truth. Did you do this experiment in secondary school? Give me a thumbs up if you did it, and a thumbs down if you didn't do this particular experiment. Lillian, you can send me a direct message later. Maybe they no say no do it. All right, don't mind me. So now, look at what I'm saying. I'm simply saying that the deviation is trying to tell you how much a ray turns from its original path. That is what deviation is all about. How much does a light ray turn away from the original path? Now, this is the path of the light. It should be moving in this straight line. But because there is an obstruction, this is a triangular prism, it bends away. This is the path, and then it moves this way. This is where it moves away from. So how much it moves is the deviation. That's your D1. It doesn't stop there. That's one thing about triangular prism. Three things happen. Now, the light will refract when it enters the prism. Now, upon leaving the prism, it still refracts again. Are you seeing it now? So this is just the diagram or the images of your triangular prism. However, for JAMB, you don't need so much information on this. There are just few things you need to remember. And what are those few things you need to remember? You need to remember that this I, let me just write it down for you, that this I here, I is the what? The angle of incidence. This is the angle of incidence. And heat is too much. That's why I had to turn off my distance. I think at a point I need to pull my shirt out. That's a miracle. I just had to. And they just took like. So now, the Paul is laughing at me. Now, R is the angle of, R1 is the angle of refraction for the first surface. Angle of refraction for the first surface. You can see there on the first surface, right? Your R2 is the angle of refraction for the second surface. That's the unique thing about your triangular prism. You know, the other one I did, this one is for rectangular prism. This experiment is for rectangular prism. Can you remember a rectangular prism now? For me, my school, we did a lot of experiments, sincerely. Like, that's why I like that school, man. In as much as the building was not too fine, like my secondary school, the building was not too, so amazing that way. But you see, in terms of practicals, man, they drilled us. Electricity, every Saturday, we used to go to school every Saturday, for experiment. The only thing I didn't like back then about the school is because of that Saturday experiment. You'll be thinking, what would you wear to school? Some of my classmates can be so wicked. There's a kind of trouser you wear to the there's a kind of clothes you wear for the weekend classes, and you will not be comfortable. They will laugh and laugh and laugh. But for the experiment every Saturday was quite amazing. So this one is for rectangular prism, rectangular what do you call it? Rectangular glass. Very simple. This very experiments. Then the next set of experiments is now this one, the one of triangular prism, where you start looking for internal deviation and all of those things. So now R2 is the angle of refraction for the second surface. Angle of refraction, second surface. We'll have a lot to do. I pray I'll meet up, and then we'll solve questions. Then the next one is your E. We'll call it the angle of emergence. Then A, are we there? Is the what? Is the angle. Is the angle. Angle of what? Is the angle of the prism. Then we'll have D, which is the what? Is the what? Angle of deviation. The angle of, so these are the angles that we'll be mentioning here, is the angle of deviation. And I have told you that deviation is what? Is simply how much the ray turns from its original path. All right, so deviation, sorry, should be DE. Deviation is simply what? How much the ray turns from its original path. All right, so always remember this. Now, key things we need to know in terms of your deviation, just key formulas we need to know, right? So remember what I said, that incident ray, it's going to be refracted, right? So the deviation is here. Second surface again, there will be a refraction. This is the normal, right? Bending away from the normal, right? It keeps going out again, being refracted. You will have last angle, which means that R2 plus D2 will give you the angle of emergence, right? And there's a relationship between this angle of emergence and the incident ray, the angle of incidence, which I'm going to talk about, right? So now, what are the formulas you need to remember at every point in time? So I've given you 3 equations. So this one will be my equation number 4, that deviation is equal to the incident angle plus the angle of emergence minus what? The angle of the prism, right? This is your equation number 4. Men and brethren, are you still following? Give me a thumbs up, please, if you're still following. A thumbs up if you're still following. All right. Oh, Paulo, go ahead.
So in the diagram, we have D1 and D2.
Okay.
So how do we put that into this formula? Let's say they ask us to find, is it the total deviation we find? Or
Yes. D.
that's
Not by.
D1 plus D2.
Not by. Sorry, you know that once I begin to buy fuel for my stomach, I'm making a mistake. So this is what it is, okay? That's a very brilliant question. Is that okay? So now, minus the what? The angle of the what? Of the prism. Now, there's something else we call the minimum deviation, right? Nikki got silver, you following? Mesa. Mesa have grown cold. What happened? Mesa, are you here at all?
Yes, my auntie's baby is disturbing. She's not around.
The baby is disturbing. You know, me, I'm a caregiver. When it comes, I'm very brutal in that area. Let me tell you what to do. Should I tell you what to
do? Talk that.
How old is the baby?
I think 3 months or so.
3 months. Yeah. You never reached my expertise is from 1 year and above. The one of 3 months. Sometimes I'm scared of carrying them. I feel like if I hold them, I might just compress them with my hands. I'm just very skeptical about those. I don't know, but that's the phobia I have. That if I hold their hands, I might break their bone. But I don't know how to start correcting my head along that. I don't know whether it happens to any other person, you know. So
when you give birth, you still carry your baby now.
When that time still there. By that time I will reset my brain. So please just try and manage and follow through. Right? Try and manage and follow through. So the equal boy, if they are a year and above, I'm very brutal when it comes to, at least by that time, I know that they are very strong enough, you know. Even the other day, I had to watch YouTube on how to change pampers. And it worked though, guys. Like I delivered. So YouTube is a very powerful place. All right, so D equal to D1 plus D2. Well, I think that I've answered your question, right? Now, we have another one we regard as your minimum deviation. But I think we should give love emoji to the women in the house, please. Please, love emoji for them. It's not easy. So for the guys in the call, I think you should give them a love emoji now, like for the ladies in the house. Their responsibility is a whole lot. I did that. I took care of my nephew for just 1 week. I nearly went mad. Just 1 week alone, So they are doing a lot. And they are very good at multitasking. You see somebody taking care of this one, doing this one, and then you wonder how they go about it. Right. So it's just amazing. It's just amazing. So for the ladies in the house, I'm rooting for you. All right. So now for minimum deviation, it is simply the smallest possible deviation that light can experience when passing through a prism. So there is the smallest deviation we can have. Is that way now? Now the smallest bending away, let's say it like a layman, the smallest bending away or bending of light, the light can experience. The smallest bending, right, it can experience is what we regard as the minimum deviation in a layman term. I said how much the ray turns away from the original path. So the smallest amount that the ray can turn away, right, from the original path is your minimum deviation. I think I've paraphrased and I've said it in different ways that anybody can understand, right? So now let me write it down now. So your minimum deviation in bracket, your senior secondary school fees is called a DM, right? Is the smallest possible. And that's where the question will always come from. If you check past the question, the smallest possible deviation that light can experience when passing through a prism. All right. So that's the minimum possible deviation when passing through a prism. Now, when do we say there are two conditions for minimum deviation to take place? It happens when the light passing the prism. What's the best way to capture this? When the light passes symmetrically, through the prism. And what do I mean by when it passes symmetrically? That's the statement you're going to see, right? At minimum deviation, right, the light ray passes symmetrically through the prism. Do you know what that simply means? It simply means that this angle here, at that point where this angle, the angle of incidence, is equal to the angle of emergence, is when we say that minimum deviation has occurred. And that is what we mean that the light passes symmetrically through the prism. Do you get the point now? It passes symmetrically through the prism. That is when we say that we have a minimum deviation. And that statement symmetrically is simply saying that the angle of incidence is equal to the angle of emergence, and this R1 is equal to R2. We'll say that there's minimum deviation. And at that point, what did I say again? At that point, light passes through the prism symmetrically. You know what is symmetric now? Equal parts. Can you remember what symmetric is? When you divide something into two, the left-hand side is a reflection of the right-hand side. It's a mirror image. I wish my video is on, but because it's them hot, so okay. So now it's a mirror image. Are we together? Do you understand what I'm trying to say now? So, but the statement I want you to remember regarding your UTME exams is when you hear minimum deviation, the light will pass through the glass light prism symmetrically. And what does that symmetric entails? It simply entails that the angle of emergence is equal to the angle of incidence, and that's the refracted ray, that's R1 on the first surface, is equal to the R2 on the second surface. That is all you need to recall, right? If that makes sense, can you give me a thumbs up, everyone? If you really understood what I just said now, can you please give a thumbs up? Right, I have it from Nikki. I have from Paul. Nikki, what's up? Okay, I have it from Lillian. Nikki, are you there?
Sir, I'm hungry. I want to go and eat.
Man shall not live by bread alone. Miss, are you following now? The baby, but the person that is quoting that scripture is eating already. Meso, are you following? Sorry, Meso, I know the baby is disturbing you, right? So later you can watch the video, okay? Sorry about that. Yeah, sorry about that. When the baby gets to 1 year, let me know. I will take over from there. All right. These things are not clicking again. Okay. So now let's talk about angle minimum deviation, right? This happens when number one, right? The light ray passes, please take note of this statement, passes symmetrically through the prism. Right? By symmetric we mean, number two, by symmetric we mean that what happens? The R1 is equal R2 and that I is equal to what? E. So I will call this my equation number what? Which equation number did I stop now? This is equation number 5, isn't it? We'll call it our equation number 5. So that's the, oh my God, what is happening here? But did you see that? You should give me a little more time. All right, so R equal to R2 and I equal to E, right? So now that is it for minimum deviation, right? So please always take note of that. It simply means that the ray enters and leaves at equal angles. So let me put it for you. 3, right? The light ray enters and leaves at equal angles. All right, are we there now? So just take note of that. And there's a formula I forgot to actually add to us here, that deviation is I plus E. I also forgot to add that R1, that A is equal to what? R1 plus R2, right? So let me add that one and call it equation 4 for A. An enemy has done this. All right. Please, are we taking note of all of this? Are we taking note of all of this, right? So your deviation is your angle of incidence plus your emergence minus what? Normal deviation minus your what? Your the angle of the prism. But if you don't know the angle of the prism, you simply add the refraction at the first surface plus the refraction at the second surface, right? And remember that deviation is the first deviation plus second deviation. But on rare cases, do you need those first deviation and second deviation? Their major concern is always along what? Your angle of what? The minimum deviation, right? That's where the bone of contention will always come, and for you to actually grab this concept of what I just gave us now. All right. So now the next thing you need to know that at minimum deviation, right? Therefore, hence, at minimum deviation, we'll have R1 equal R2. Therefore, we have, if you have that, that means you can have something like this. You have that R1 is equal R2 equal to A all over. Let me not do this so I can show you something. Now, if R1 is equal to R2, right? Okay, let's start from here. I don't want to confuse anybody, step by step. So recall that R1 plus R2 is equal to what? The angle of the prism. Now, but at minimum deviation, we'll have that R1 is equal to R2. Does it make sense now? Right? So now what that means, which we can now say that we now have that R1 plus R1 again. So anywhere I see R2, I can plug in R1. Does it make sense? Anyway you want to do it is equal to A. So that what? 2R1, right, is equal to A. So divide both sides by 2. Divide by both sides by 2, right? So it means that what? R1 is equal to A over 2. Or R2 is equal to A over 2, right? So generally, we can say that R1 equal R2 equal A over 2. Yeah, it's clear, right? You get what I did there, right? A thumbs up if you understood what I did there, please. Good. Titi gave a thumbs up. Paul, you there? Paul, you there? Yeah, makes sense. Confidence, are you there? Justice, are you there? Meso, are you there? Nikki Got Silva, hope you are following. So you understand what I did here? That's for at minimum deviation. That's how to get this, right? So at minimum deviation, we're expecting this very equation, right? And that will give us our equation number what? Our equation number 6. All right. So that said, now we're going to connect the refractive index of a prism now. So how do we get now? The last one is the refractive index of a prism. Refractive index of a prism. Not the last. I also have to touch the total internal reflection. So refractive index of a prism. So now how you can connect the both of them, right? At minimum deviation, right? The formula for your refractive index of a prism is simply that n is equal to what? Sine. Are we there? Sine of open brackets, right? Deviation, that's dm, right? Minimum deviation plus a all over 2, close bracket, all over sine, a over 2. So that's the formula for your refractive index for a prism. Is that okay? So for a prism, you are expected to have this. Are you there now? So n equal to the sine, right? You have dm, which simply means the minimum deviation plus the angle of the prism divided by 2 all over sine of the angle of the prism divided by 2. So that's the refractive index of the prism. And that will give birth to the final equation. So all those things are connected. I don't think you need to cram anything. But the ones I want to always remember is what is the condition for minimum deviation? Remember that. What is the formula? What's the law of refraction? Remember that. So what's the formula for your refractive index of a prism? Also remember that. Then finally, what happens at minimum deviation, like I rightly said. So these things are very, very important. Remember that n is a refractive index, right, of prism. So where n is the refractive index of prism, then what again? A is the prism angle or the angle of the prism. Then dm, I've explained how to estimate your dm, right, is the minimum deviation. All right, everyone, hope we are following till now. Everyone, hope we are following till now. Can you give me a thumbs up if you are still with me? Very good. Thank you, Lillian. Miss, are you there? Anyone following should give me a thumbs up, please. All right. Let's look at total internal reflection. So when you are talking about total internal reflection, you are making reference to two key things, okay? Two key things comes into play, or two key conditions are the conditions that must be considered when we are looking at your total internal reflection. Number one, it must be traveling from a dense to a less dense medium, right? And there's something I explained earlier. What really happens here is, let me see if I can copy that diagram so it will make more sense to us, please. Let's copy this diagram. Let's copy this diagram so it will make more sense when I start explaining. So now, remember what I said. For total internal reflection, what happens is that you are traveling from a dense to a less dense medium. Is that okay? Right? So medium one in this case is going to be what? Is going to be what? Dense. And medium two is going to be what? Less dense. Right? And in that case of your dense and your less dense, do you know what happens here? Like I said, what happens is that the reflected ray will be bending towards the normal. Sorry, will be moving away from the normal, I mean to say. So that's the first thing. As you keep increasing the angle of incidence, the refracted ray is moving away from the normal. It will keep moving away till it now becomes an angle of 90 degrees. That means that this guy now lies at an angle of 90 degrees. And beyond that very angle, the ray is now reflected backwards. Instead of bending away, it is reflected. So that's what we now call the critical angle. So the critical angle is that angle beyond which, right, if you pass that very angle, you now have total reflection. Do you get the point now? Do we understand now? Can you give me a thumbs up? Paul, give a thumbs down. Hey. Okay. Okay. Look at what I'm saying. We have medium one and we have medium two. Now, the more you increase this angle of incidence, because the light ray is traveling from a medium that is denser to a less dense medium, it is expected that this ray will be moving away from the normal. This is the normal, right? It keeps moving away. Do you understand? It keeps moving away. So now, look at what I'm saying. Let me see if I can replicate this image now. Let's try. This is how it should be. But the more we increase the incident angle, right? The more we increase that incident angle, we're going to get to a point where it becomes 90 degrees. Look at all I'm saying. Now, I have the second part of things, right? Let's keep it right here. I have the second part of things. And imagine that we have increased this incident ray. Let's increase it a bit. Let's increase it a bit. Then let's bring it down. Are you seeing that we've increased that angle now, right? Let's increase the angle a bit. Now, if we've increased that angle, now what happens is that the more you increase the incidence ray, the more this guy bends away from the normal. That's what I'm trying to say. It bends away. So now, it will now look like this. It keeps bending away from the normal, right? But you know that I wish this end is fixed. If it is fixed, it would have been easier for us. Okay? So now, it keeps bending away from the normal, moving right away from it. Do you understand what I'm saying? So as I'm increasing this guy, as I'm increasing this our friend right here, as we increase this guy here, this one is moving away from this red line. Are you seeing it now? So the more this one bends, the more this one moves up like this. And why is it moving up? Because I'm traveling from a medium that is dense to a less dense medium. If you keep doing that, it gets to a point where this refracted ray now becomes angle 90 degrees. Let me show you what I mean by angle 90 degrees. Sorry, I'm trying to copy everything so that nothing is left behind. All right, so let's copy. Then let me make some corrections here. Let's remove this. No. Wrong thing to do. Okay, I hope you get my point now. So we'll have this wiped out. So what is happening here? We are increasing our incident angle. So from here to here remains our I. Then, then from here to here, from the normal to this place is my reflected angle. So now what happens next? The next thing I want to show us now is what would happen if I keep increasing my angle of incidence. It will get to a point, are you following, guys? It will get to a point where this guy will now align at 90 degrees. The refracted ray is going to align at 90 degrees. So let's pick it up. Then let's move it to align properly. So at that point, it now becomes this way. Do you get what I'm saying now? Because we are doing what? We are increasing our angle of incidence, right? So let me see if I can just move this one a little bit again, just small, just a little bit, just small a bit, right? Might not be as big as what I'm showing here, right? So what happens here? You've seen that that angle is moving. This is still your angle of incidence. You are increasing the angle of incidence, and at the end of the day, you see that this angle of your angle of refraction now is 90 degrees. Can you see that now? Remember that this is your incident ray. This is your incident ray. Then this is your what? Your refracted ray. This is your angle of what? Refraction. Remember that angle of refraction is the angle between the normal and the reflected ray, right? So that keeps happening to that point where this thing becomes 90 degrees. And if you increase this angle further, what will now happen is that this ray is now going to be reflected. So let's try that. If you are still confused at this point, I don't think nobody's confused at this point, isn't it? It's making sense now, right? Because I'm taking time to break the steps. Titia, is it making sense, Titi? Good. Every other person, Lillian, are you on the call? So you keep moving that, you keep increasing that. That's exactly what is happening, right? I know that this topic will take a lot of time because it requires too much diagrams. So now remember, for this thing to happen, the medium, they must have to be what? They have to be what? Dense and what? And less dense, right? So the angle of incidence in the denser medium, right, must be what? Greater than the critical angle, right? So now for that critical angle, remember that angle at this point, this I now, I here is equal to what? What will I call that I? Will now be equal to what? Equal to C, right? So I here, I equal to the critical angle. So that angle at which the refracted ray, the angle of incidence becomes 90 degrees is what you regard as what? The critical angle. The angle at which the incident ray, right? So the angle at which the refracted ray equals 90 degrees is what we call the critical angle. So now, for us to do that, I think this is no way I should actually label that, right? It should be all part of it. So now, let's clean this here. Let's clean this here. So the refracted ray at this point will have that. Let me use a red marker to do that. So here, at this point, we'll have that I is equal to what? Critical angle. And that R is equal to what? 90 degrees. Now, if I rotate that guy further beyond the angle of what do you call it? Beyond that 90 degrees, let me move it a bit again, just a little bit, right? So if I move that guy a little bit here, I'm going to have this, right? So that angle here we'll still have an angle of incidence here. But at this point in time, something happens to our refracted ray. What will happen to our refracted at this point? Sorry, I mistakenly cleaned the one I didn't need to clean. All right, still the same problem. Good. So now what happens is that the ray will now be what? Reflected. This is your what? Total internal reflection. Do I have people in the house that understood what I said now? Do I have men and women in the house that everything now makes sense to? Right, good. So that's what happened here. So for total internal reflection to occur, number one, the light must be traveling from a dense medium to a less dense medium, and the angle of incidence in the dense medium should be greater than the critical angle. You can see that I here, I is greater than what? The critical angle for it to what? For it to happen. So if that does not happen, then you cannot talk about total internal reflection. Is that okay? So the refracted ray is going to be what? At the critical angle. Then you can now proceed to get that. Is that okay? All right. So now conditions. Let me now give you conditions. Conditions for this to happen. Conditions. Condition number one is that light must be traveling are you there? From a dense to a less dense medium. The next one. Is that the angle of incidence, right, in the denser medium are you there? Must be greater than the critical angle. All right, everyone. I hope that makes sense. So these are the key things you need to remember about your critical angle, right, and all of that. Okay. So now that means that the formula is going to change, isn't it? Right. So if I'm using air to glass, right, the formula is going to change. That's thing I told you about. For refraction to happen, if I have that that A N G is equal to what? Sine I over R. It now means that what is the next thing that will happen now? It means that G N A will now be equal to what? 1 over. Are you seeing it now? Sorry. This is sine R. 1 over what? Sine I all over what? Sine R. Okay. So now this means that when you are traveling from glass to air, because glass is denser now, you're going to have what? Sine R all over what? All over. Or the other way around. Let me move the other way around, right? Let's move the other way around. So it will make more sense to us. All right. So we have that sign that what do you call it? G and A will be equal to what? 1 over, are we there? 1 over A and G. Do you understand this formula I wrote here? G and A will be equal to 1 over A and G. Remember that this one is from what? From glass to air, right? from glass to air, which is from denser to less dense, right? So this is equal to this. Thank you. Any other one following? Are you there? Are you following? Tita, are you following? Yeah, good. Nikki, are you there? Hope it's making sense, yeah? Good. Meso, are you following? Good. So if you invert this, right? Now, remember that the left-hand side, remember that the left-hand side is what? That's, how will I put this for us better now? How do I put this better for us? Okay, just take note of this. When we start solving past questions, I think to make more sense, let me not use much of notations. So just take note of this. That is exactly what will happen. And remember that at reflection, that sin r is equal to c. Remember that. That at that point in time is equal to c, right? Sin r, sin I is going to be what? C. That angle of incidence is going to be what? C at that point in time. All right. So that is it for total internal reflection. So I think we can now get our hands dirty with the questions that are sent to us. Any questions so far? Any questions so far? I believe everybody is following and I get the entire concept. These are all you need to be able to solve the questions that we'll be tackling now. Paul, did you send anything?
Yes, sir.
Okay. Question. Like it many. That's to tell you that those guys ask questions a lot from this. All right. So let's go. See problem. I didn't stop sharing my screen. These children will soon see my secret one day. I'll have to come one day. Before you know it, you'll be online. God, I beg. Right, but nothing is happening anyway. I have trusted men and women, isn't it? Let me create more of these things so as to accommodate all the questions. I think there are about 27 of them that Paul sent, so that each one will take a particular place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right here, 16, 17, 18, 19. I think that's enough. So let me insert all the questions. All right. Paul, well done. So far, so good, bro. So far, so good. But I love the questions you got here, man. Very amazing questions, bro. Don't worry, I'll visit Lagos soon. Have you stay in Lagos? Have you open? Don't worry, anywhere you stay, I will come and find you there. Don't worry. A great guy. And very soon I'll be fully in the West. Don't worry. So you guys are still in the group now. When it's time, I'll let you know. Is that okay? Sister, don't say you give me thumbs up. Prophetically, we are going to the West. All right. So now, you guys are popping champagne, are Okay. So you guys are not talking. All the Igbo brethren in the house are not saying anything. All right. Okay. You people should be coming down. The Igbo brethren are not saying anything. All right. So let's proceed. A ray of light. Oh, can you see my screen? You can, right? Yeah. The first one says a ray of light which strikes a glass slab from air at a normal incidence passes through the slab. Deviated and A says deviated and undisplaced at a lower speed, undeviated and undisplaced at a lower speed. So go over, just what's your answer, guys? Very fast. We have a lot of questions that Paul sent here, plenty of them. And I'll be very glad to walk you guys all through them, right? So plenty of them. Anybody answering, or should I go ahead and make some reference on that, and then we'll go to the next, because there are a lot of questions we need to tackle. I think it is D. So Meso have transferred that thinking to you, right? A ray of light which strikes a glass slab from air at normal, right? Incidence passes through the lab. Are you seeing it now? So look at what they are trying to say here. Let me answer. Right? You have, let's say this is the slab. This is the slab. Are we together? This is the slab. Right? Here, this is air. Then this is glass. Then it says that the ray strikes from air at normal incidence, passes through the slab. Now, normal incidence this way is a straight line. That's what they are trying to say. That's the angle of deviation, the angle of incidence is straight up. Remember, this is your normal. And this is what the angle of incidence is trying to say. So the angle of incidence here, angle of incidence is equal to 0. Do you get what I'm trying to say? It goes straight up. And at that point, what happened? It doesn't bend. Do you get the point now? It doesn't bend. In as much as it's traveling from what? Yeah, B. Right? So now there's no angle. So what do you think should be the answer now? Right? Remember that another thing you need to know is that light will travel faster in air and slower in glass. So we know already that it's going to be what? Undeviated. Number one. One is what? Is undeviated. There's no deviation. It keeps traveling in a straight line. Right? Because of what? Incidence angle is 0, right? So it just straight up. So there's nothing like that. It doesn't bend. The light doesn't bend. It just keeps traveling, right? Now, how about these displacements? We cannot be expecting displacements when the angle of incidence is not inclined. It's just straight up. So now, 2, there's nothing like displacement, undisplaced. Then the third one you need to know is that light will travel faster in air than in glass. So Meso, you have it. Okay, so do you get the point now? Since the angle of incidence is just straightforward, so that light travels on a straight line, undeviated. It cannot bend. Nothing will happen. The guy will kochiri. You understand? Because the angle of incidence is what? 0. It's not inclined at an angle. So kochiri means it's going to stand still. Nothing will happen. Is that okay, guys? I think we've answered that very question. Right?
So what's on this place?
Eh?
What's on this place?
Undisplaced. Okay. Now, when I mean undisplaced, look at what I'm trying to say. If this ray is coming towards this direction, let's say that the angle is inclined, right? Let's say the angle is inclined and it's traveling through an inclined angle. What happens right here? What happens to the refracted ray? There will be a bending away, isn't it? Are we together? There will be a bending away. But in a case, my judgment of this undisplaced is because I know that this guy is traveling in a straight line. So I don't expect anything to be displaced. Nothing will happen. It just keeps traveling. If it's undeviated, if the thing does not bend, nothing will be. You know what is displacement now? There will be a movement, isn't it? You get my point now? So, but since there's nothing like that, it didn't bend, it was just moving in a straight line. Remember, a body at rest or a body traveling in a straight line will keep traveling in a straight line unless acted upon by an external force. Do you get the point now? So the light doesn't bend. R equals 0. Exactly. Incident also equal to 0. So nothing happens. Is that okay, Paul? Meso is on fire. Look at the chart. Meso is giving bomber to bomber with her 3 months old baby that she's taking care of. Maybe small, you know. All right. So that's for that, guys. Thank you, Paul, for that question. That's a brilliant one. Good. Calculate the critical angle for light traveling from glass to air. From what? Glass to air. Now, refractive index of glass is 5/3. Remember what I told you. This is simply what? This is A N G. They said is equal to what? 5/3. Are you seeing it now? Now, but for critical angle, reverse will be the case. For critical angle, what happens at critical angle? Can someone tell me now? It's medium will not be what? Medium will not be what? From glass to air. Do you understand now? Therefore, refractive index now, index of air will now be equal to what? 3/5. Because that's what you need. I don't know if I'm making sense, guys. Good. Good, Paul. Anyone confused? Let me clean again and start from beginning. That was why I was shouting that time I was introducing that stuff, because I know I'm going to see that kind of question. I was trying to hit it bomber to bomber for you to understand what I'm trying to say in terms of the swapping of this thing. So now, if the refractive index of glass is 5/3, do you know what it means? That the traveling is from what? From air to glass. Remember now, guys, remember now, isn't it? If you are telling me that refractive index of glass is this value, it simply means that we are traveling from air to glass. Can you give me a thumbs up if you agree what I'm saying? Good, 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 good. Okay, so I'll use this question to prove a particular formula for us. I was trying to prove that formula before, but I said, let me use values. If I use values, it will be more easier for us. Is that okay? Now, remember that it was Snell's law. How will I, God help me? Remember that for your Snell's law, we have that N, are we there? That N is equal to what? Sine I all over sine R. Now, refractive index of glass. Right? Which means air to glass. They gave us to be equal to what? 5/3. Now, but they said from glass to air now. It's traveling from what? From glass to air. From what? Glass to air. So now, it means that now from okay, let's put it up this way. I have critical angle. Calculate the critical angle, which is sine R. All right. Calculate the critical angle of the light traveling from glass to air. I'm trying to find an easier way to prove this thing for you guys. That formula I need to use. So the refractive index is 5/3. All right. If the index is 5/3, I need to get my critical angle, which is my sine I. Right. R is 90, isn't it? Okay. Okay. So now, from denser to dense medium, which means at this point we are looking at what? Glass to air. From glass to air, it means that the refractive index of air now let me maintain a particular, you guys, because of how to explain me, I'm not confusing, looking for a way to make things easier for you guys. Let me just do what I have in mind. People that understand will explain for those that don't understand. Right? I have that n, which is what I think we should use. I'm trying to prove that formula actually. I'm trying to prove that formula for you guys to understand how that formula came to be, right? So you have n equal to sine I over what? R. But then when you're moving to a heavier medium from denser to the less dense medium, right? What happens is that, like I told you, your refraction now, your sine R is going to be what? 90 degrees. Do you get the point now? And your angle of incidence is what we are looking for. So let me just go ahead and do that. Then later I'll bring in this, your refraction of index, right? Let me just go ahead and prove. Anyone that understand will understand, right? Now, at critical angle, we have that R is equal to what? 90 degrees. So that means that we have that N is equal to what? Sine I all over what? Sine 90. And you have that I will now be equal to C. So that's equal, this is equal to what? C, right? Now, what I will get now is that sine C is equal to what? N sine 90. Now, sine 90 is equal to 1. So sine 90 is equal to 1. So that sine C is equal to what? Equal to N. Now, you are looking for the critical angle C. So C will now be equal to what? Are we there now? Is someone following? Give me a thumbs up if you follow to that point. Good. I'm looking for C, right? So what will I do? I need to do the sine inverse, isn't it? Or let me not do the sine inverse yet, right? Let's not do sine inverse yet. Maybe I can just skip it and pipe low at that point, right? So now, let's multiply. Sine 90 is 1, so I have times 1 right here. So I'm trying to look for C. Okay. Sine C. C will now be equal to sine inverse of N, isn't it? Good. I want to prove that formula so that it makes more sense. Good. Now, but remember something, we have N times 1. But recall, right? Are we following now? That N at this point in time is equal to what? Has to do with what? That of the what? The dense medium. Are we following? The dense medium all over what? The less dense medium. Are we following now? Where this N now is simply from what? A to G, class to A. Now, if I now want to get my, I need to create a new page. If I want to get, it will now be the other way around. If I want to now get N from glass, air to glass. Oh yeah. Glass to air will now be equal to what? 1 over that thing I wrote before, which is your what? A, N, G. Do you understand what I'm trying to do now? So therefore, I'll have that sine C will now be equal to what? 1 all over what? 1 over N. Because remember that what I had here before, that sine C, let me pause it right here. Sine C will be equal to N for a normal traveling, guys. But now, normal traveling, which is from air to glass. But now, when you are now traveling from a denser medium to a less dense medium, you now invert it. All this, my grammar is just trying to say that this is now what you use for total internal reflection. Where this one, we can put this to be our what? AG, air to glass. Does it make sense now, guys? Everybody, a thumbs up. Yeah, Titi gave a thumbs up. Who again? Who again? Yeah, Lillian, a thumbs up. Beautiful. So now, for this question, they gave us that from air to glass. air to glass is equal to what? They gave us 5/3. They gave me 5/3. This is 5/3. So that I have that C will be equal to what? Sine inverse of 1 all over 5/3. So this will give us that C is equal to sine inverse of what? 3/5. So go ahead and punch this. Meanwhile, let me now add that formula I wanted to prove for you guys earlier. But thank God for this question. I know that while solving a problem, it will be easier for me to bring that in, right? So therefore, we have that sine C, remember, is equal to 1 all over what? An, or let's call it N here. Let's call it N. But remember that N is for what? A and G. Is that okay? So take note of this particular formula. Let me call it equation 8. I wanted to bring it in here, but I said no. Let's leave a question to bring that in. Everybody who has punched that very value for us, anyone who has punched it for us, so we can go to the next question. Sine inverse of 3/5. Very fast. There are a lot of questions to be handled today, okay? Anyone? Paul, even if others don't do it, go ahead and send it. Yeah, give me the value. What's the value now? This guy is here. Doesn't mean that nobody has calculator or what?
So it's in the chat.
It's on the way you okay.
That is 36.9.
You tell me now. My eyes will no longer always be on the chart now. 36 point what?
9.
36.9. So that's C equal to what? 36.9 degrees. So that's for that. So anytime you see that question, simply go straight and apply the formula. You don't need to be proving all these things I proved. I just wanted to show you guys something, right? That N over G is dense. ANG, sorry, this should be the other way around. Is less dense to dense. So now, if you now want to get that of denser to less dense, you now be over the other one. All right. So that had been done. They said, what is the phenomenon where a wave changes direction as it passes from one medium to another? So that shouldn't be a question at all. We all know the answer, right? It's a refraction, isn't it? It changes direction. So this is not a question at all. So this is a refraction. Let's go back to the next very fast. Let's see what we can cover before your next class.
Is this kind of question we want to see? Which one is not a question?
What is the critical angle of light traveling from water to air? Refractive index of water is 4/3. As always, C is equal to 1 over 4/3. You do, sorry. As always, you have that C is equal to sine inverse of 1 whole number 4/3. You get your answer, okay? That's for that. Calculate the angle of minimum deviation for a ray which is refracted through equiangular prism of refractive index 1.5, 1.4. If it's equiangular, do you know what it means? That the angles are equal, right? Very important. So once you see that statement equiangular, it simply means that the angles are equal. Now, what does it mean? That our A is going to be 60 degrees. Is that okay? So what's the formula I gave you earlier for that? Angle of deviation. There's a formula we have for that, and we're looking for that very angle. So let's quickly make reference to that. Okay, remember the formula that says that N is equal to what? We have sine. Let me reduce the size of the pen a bit. We have sine, open brackets, of what? I used A plus dm, which is the deviation. divided by 2, then open brackets, we'll have sine A all over 2. So now, since they said equiangular, right, it means that it has equal angle. And that means you're going to have 60, 60, 60, 60 all through, right? So now equiangular, are we together? It has all sides equal, right? So remember that if it has all sides equal, it means that A equal B equal C. So we can say that A plus A plus A equal 180 degrees. Is someone following me? Equal 180 degrees. So that 3A is equal to 180. Divide here by 3, divide by 3, so that A is equal to 60 degrees. All the angles are equal. So which means that A, for that distant angle of the prism, will be equal to what? 60 degrees. Now, let's solve our question. So N is equal to what? They gave us N. I'm going to plug it in. Thank God there's light. It won't kill me here. So you have that here. I will follow in, guys. Well, I hope my video is off. Okay, good. We have that A here is 60. Then N is equal to what? They gave us N to be 1.4. So let's quickly solve the equation. So we have 1.4. Are we following, guys? So I have 1.4 is equal to what? Sine, open bracket, A is what? A is 60. So this will be what? 60 plus the formula. I'm looking for the deviation divided by 2, right? You close brackets, if that's the case. Okay. Then all over, I have sine 60 over 2. So now, what's the next step I'm going to take? I have that here is 1.4 is equal to what? I have sine right here. So for that sine, we have 60 again plus the angle of deviation divided by 2, we close brackets. This will give me what? All over, this is 30. Let me reduce what I have here now. This is sine, okay, let me keep it that way. So this is sine 30. Sine 30 is 0.5, isn't it? So now I'm going to have, how do I break this off here? Sorry, let's break this off here so that we'll have space, please. All right, I've copied it. Later, I'm going to paste it. So now sine 30. So I'm going to have that 1.4. 1.4 will be equal to what? Sine, open bracket, 60 plus dm, all divided by 2, close brackets, all over what? Sorry, I'm rushing. That's why everything is now. I want to cover more questions. This is 0.5. So 1.5 times by 0.5 is equal to what? Equal to sine, open bracket, 60 plus dm, right, all over 2. Please pay attention to see how I'm going to solve this question. Please pay attention. Now, 1.4 times 0.5, I have to use my own calculator. I won't wait for you guys again. That will give me 0.7. So this is 0.7, right, is equal to, what do you think I'm going to do right here? Who can suggest? Do you have any idea now? Don't worry. Let me finish it up. No idea from anybody. Hold your idea at this point. So go to the exam hall, apply this, right? So what I'm going to do, I'm going to take the sine inverse of both sides. So I have the sine inverse of 0.7 will now leave me with this place. The sine will be removed. I have dm all over what? All over 2. And sine inverse of 0.7 will give us sine inverse of 0.7, shift sine 0.7 will give me 4.427. So, but I think we can, okay, let's continue. So this is 4 4.427 is equal to 60 plus dm all over 2. So let me cross multiply. When I do, I'm going to have 4.427 multiplied by 2 is equal to 60 plus dm. 44.427 multiplied by 2, that will give me 88.854 minus 60 is equal to dm. That's the minimum deviation, right? So that said, we're going to have that our deviation will be equal to what? I will follow you, men and brethren. It's 8.854, good, minus 60, right? That will give me equal to what? 28.854. If you see this question in the exam hall and you don't answer it, oh Jesus. What you just notice that somebody will give you heavy knock from nowhere inside that exam hall. You will just feel it heavy knock coming from nowhere. You don't even know where it is coming from. So now that's the particular value you have there, right? And that answer, if you approximate, you have 28.89854. So if you check, there's no 28, which means they are approximated to the nearest whole number. So when we approximate to the nearest whole number, we should have what? 29 degrees. All right, so that has been solved for you, right? Good. Any question, guys? Any question? Any question? All right, so this one says that when light crosses a boundary between air and water, the following quantity of light remains the same. When light crosses a boundary between air and water, the following quantity of light remains the same. So which one remains the same when light travels from air to water? Remember, this is a different medium, right? We know that the speed cannot be the same because the speed is going to change, isn't it? It says D, frequency, all right? Who again is supporting frequency that the Mesa gave us? Any other person supporting frequency? Tilola is supporting frequency. Nikki Gotilva, are you supporting frequency? Paul said D, frequency. Okay, Paul is supporting D. Lilian is supporting D, all right? Okay. So why are you guys supporting D? All right, so and you guys are correct anyway, but I want to hear one person that will give us the reason why it doesn't. Who can tell me? One statement. People that said D, Titi, give me the reason very fast. We have barely a few minutes to round up by 12:30. Titi, can you give me the reason why you said frequency does not change?
Okay.
Your voice,
I don't
your voice is low, please.
see something like that again.
Okay, in the absence of that, it's not saying anything. Remember that frequency is more, it depends on the source of light itself, right? It depends on the source of light, not where it's not crossing the boundary, right? So that one is entirely off. Well done, guys. Now the next one says light of frequency this traveling in air is transmitted through glass of reflective index 1.5. Calculate the frequency of the light in the glass. I know I didn't give any formula connecting frequency and all of this, but we did our wave, and there's a connection between the refractive index and the speed of light, right? I've actually explained that there's a connection, right? Speed of light and velocity of light in the first medium over velocity of light in the second medium. There's a formula I give right here, which we are going to use to connect it together. Velocity of light in medium 1 over velocity of light in medium 2. Remember that very formula is going to come to play for you to be able to answer that particular question. I don't know, are there people that wants to give it a try, or should I go ahead and solve? Anyone? Give me a thumbs up if you are trying it out. And remember something, you guys answer. Let me see. Based on the answer you gave me in the other one, let me see who answered this question. The answer you guys gave me in this question, let me see who will use that idea and answer this. There's nothing much you are solving. Let me see. They said frequency. Kai. God. B, yes, now. B.
Frequency will remain constant, so
It
the
will remain
answer is
exactly. So now answer them for the first time. You guys are funny. You guys are taking time because I say someone should solve. Everybody's now confused. But you guys said something here that frequency is
and I
constant.
wanted to solve it.
God of miracle. This is my students. So now you answered before. Frequency does not change. Okay. So now that answered. Let's go to the next one very fast. They said light of wavelength, this, in vacuum passes through a piece of fused this, and what is the frequency of the light in the is it quarters or something? Yeah, they gave us the speed of light, right? They gave us speed of light. Remember, they said light of wavelength is this in vacuum. They're giving us lambda, passes through a piece of this. They give us a refractive index. They give you the speed of light, and they are asking for the frequency. So what will it be? Very fast, guys. Anyone trying this? Or you guys want to be confused again? Then we'll have lots of questions here. Let's see how far we can go. If you know you are solving, give me a thumbs up. Always remember that frequency does not change. Always remember that frequency does not change. Is that okay? Always remember that frequency does not change, right? So there's nothing you are solving there. The only thing you need now, they give you refractive index. So remember the formula we learned earlier before now. What formula was that? Remember that V is equal to what? F lambda, right? Now, but V is equal to what? Speed of light at this point is equal to C now. V is equal to C, right? Which is our speed of light. So that means that I have 3.0 times 10 raised to the power 8 is equal to what? Is equal to the frequency there. What am I looking for? What's the frequency of the light in the other one, right? So now, is equal to what? V. Are you there? A. Meso said A. Good. Thank you. Thank you, Meso. Thank you for saving me that stress, right? So when you have that, you just divide through by lambda. Remember that this thing means nano, right? Times, this is F times what? 589 times 10, that is nano, right? To the power of -9. Make F subject of the formula. So you have that 3.0 times 10 raised to the power 8 is equal to what? 589 times 10 raised to the power 9. You have no business with the refractive index. Why don't I have business with that? I have no business because frequency is always what? Constant. Is that okay, guys? So that means our answer is going to be what? A. Anybody confused? Nikki Silva, are you following? Justice, are you in this class? Even if the place is noisy, can you unmute yourself and let me hear your sound? I've not heard anything from you from the beginning of the class till now. Justice. Or you logged in and kept your phone in your pocket. This is quite interesting. All right, next one. They said a ray of light is incident on the surface of water at an angle of 30 degrees. Calculate the deviation suffered by the ray in water, right? They gave us the refractive index, right? They gave us the refractive index. They said incident on surface of water at an angle of this 30 degrees. They give us the incidence ray, and we are asked to calculate the deviation. So what will it be? We are asked to calculate the deviation. What will it be? Anybody with an idea? How do you connect the angle of incidence? I gave you a formula for deviation. They didn't call it minimum deviation now. You just said it suffered a deviation, right? You just said it suffered a deviation. And they said a ray of light is incident on the surface. So how do you calculate the deviation suffered? Now, remember there's a formula I gave us earlier. Who can remember that formula for deviation? Let's go back. Let's go back to the formula. There are two formulas I should have given you. Oh, sorry, I didn't include that very formula. I only gave you the one for triangular prism. So sorry about that. I didn't give you that one. So please, for something that is not a triangular prism, yes. For something that is not a triangular prism, right? What you're expected to do at that point, look at what you are going to do. So sorry, I didn't include that. I was carried away by a minimum deviation. I'm the prism that I didn't even do that. So please, when it comes to deviation for any other thing aside, where is that question now? Anything aside what we are doing now. So what you are going to do, are you listening, please? Use this formula that says that the deviation D is equal to what? The angle of incidence minus what? R. Are we together now? When it's just a normal, let's say, rectangular prism, all right? So, but when you're dealing with all those triangular, rectangular block or glass, right? Just use this. But when it comes to triangular prisms, please use the other one I gave you, all right? So remember that they gave us the index already. So N is equal to what? Sine I all over what? Sine R. That's good to solve past questions. Open our eyes to things we forgot. This is 1.3 is equal to what? An array incident on the surface of water at an angle of 30. So this is sine 30 divided by what? Sine R. All right. So that said, what's the next step? Hope we are following, brethren. It means that sine R times 1.3 is equal to what? 0.5. I'm going to divide both sides by 1.3. Divide both sides by 1.3, here by 1.3, 33. Please, this is 0.5, not 55. So that sine R is equal to 0.5 divided by what? 1.33. So when we do that, we can now say that sine inverse, that R, A, Paul said A, good. So we have that R, let's check, is sine inverse of what? 0.5 divided by 1.33. So shift sign, then I'll have that R is equal to what? Shift sign 0.5 all over 1.33. That will give us 22.082 degrees, right? So now with that, I can estimate what I need to do so that D is equal to what? This is 30 degrees minus 22.82. So that D is equal to what? 30 minus 22.82. Is it 22.82 or 22.082? Sorry, 22.082, right? 082, 30 minus 22.082. That will give us D equal to 7.918. So that D is equal to what? 8 degrees. All right, makes sense. Paul, well done. Right. Hope we are following. So I just introduced one more formula for normal this thing that is not triangular prism. Please take note of that. Their deviation is angle of incidence minus what? Your reflection, to know how far you moved away from the journey the light is traveling. So please, it is important to know that for this guy, they are simply asking you, remember that on a good day, this guy should keep traveling this way. It should keep traveling in a straight line. Are you seeing it now? It should keep traveling in a straight line. So the deviation is how far, how much did this guy move away from what the normal journey it should be going? Is that okay? So here is your D. All right. So to do that, you subtract. So D minus I, D is equal to what? I minus R. Please take note of that as you go. So that's your deviation. All right. I hope that makes sense to you guys. So let's continue. Is Mr. Kule here? Has he joined? Not yet, right? Just come through. Check. I don't think so. All right.
He's here.
Is there?
Yes.
Okay. Mr. Kunle, they deliver like Hebrew women. 12:30 is in class already, waiting for you guys. I think we should give him a thumbs up, isn't it? No, a love emoji at this point. We need to give him a love emoji. Yeah, it's not easy to deliver like Hebrew women. Makes sense. All right. So I think the remaining, you guys will handle. Yeah. So you guys will handle the remaining ones. It's still the same concept. If you see anyone I don't understand, just quickly you can send it across. It's the same thing. What is the critical angle of the incidence of this boundary? The same question. For total internal reflection to occur, what is the condition? I've explained what the condition is. For total internal reflection to occur, we've done that. The next one says reflective index of medium M in the diagram is what? The only thing you need to pay attention to, this 60 here will be angle of incidence, 90 minus 30. Here will be angle of refraction, 90 minus 60. So here should be 60 degrees. Here should be 30 degrees. So pay attention to that because they didn't give you the actual angle. A thumbs up if you understood what they did there to confuse you. A thumbs up if you understood what they did there to confuse you. Good. Yeah. So there's something they did there just to confuse you. All right. So now the next one says calculate the refractive index of the material for the glass prism in the diagram above. You're looking for N, right? So remember the formula here. This is your okay, from here to here. Good. So this very angle here, this is your deviation D. Is that okay? This is your deviation. This is your A. This is the angle. So apply that formula that said that N is equal to sine of A plus dm all over 2 divided by what? Sine what? A over 2. So you get the question, okay? Solve that and get your answer, okay? So this one says angle of refraction R, calculate the angle through which the ray is least deviated, all right? They've given you everything that you need, the same formula, but this time around, you are looking for what? dm. Give me a thumbs up if you understand what I'm saying. Let's give me a thumbs up. All right. So just look for the DM. You have your N and every other thing you need. All right. The operation of optical fiber is based on the principle of what? You go check it out. All right. And do that accordingly. When you hear optics, what does it have to do with? So your assignment, men and brother, I think that's all for now. Displacement of producing glass, thickness, T, refractive index, N, when viewed through a glass, the same concept along there. So Mr. Kunle, I think you can light of velocity, blah, 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 your assignment. If your assignment, what is critical angle at your assignment, all right? So area of light, your assignment, okay? Total internal, your assignment. So all of these one. Assignment, okay. Get to and do well, okay? Why are you guys laughing? All right, all the best. Mr. Kula, I think, like you said, the mock now, maybe later within the week. Can you hear me?
Yes, I can hear you.
Yes. So I think later within the week, you should prepare for your biology mock. All right, so that every question, every topic you guys. Oh, I was saying that the mock for them, for the chemistry and biology, like you said, based on the topics you've done with them so far, like you said.
Okay. So when should the mock hold? Which day are we going for?
Makes sense. I'm saying like I already so that it's not too long for them. That they actually. Well, let's see. Okay, so let's say you are now